the actual video corner blocks the information. I don't know how you work that.
Okay. Are you seeing the control bar at the bottom?
Are we seeing the control? I'm seeing, you mean what slide we're on?
No,
No, I have
we're
a,
just
I
seeing
have
the slide down. We don't see the bar on the bottom
a,
that you
okay,
have.
good. All right. Uh, well, let's get started.
Sounds great.
So this really should have been, I think, before 5, but we're going to talk about the actual physical components. So we'll go over resistors and capacitors and diodes, transistors, vacuum tubes, and batteries. So resistors are made normally from some form of carbon that has a high resistance, and by controlling the length of the carbon and the width of it, they can control the resistance. Older resistors used to be made purely of some carbon mix. Uh, Today, they tend to be either what they call thick film or thin film, where they actually plate a carbon film on a uh, essentially a little cylinder or tube, and then they can laser etch that to kind of make a spiral to get the length that they need and the width to control the resistance, and they can get it down to a tenth of a percent. The other type of resistor, um, it's called a wire wound, and it's actually uh, a high resistance wire, usually something like nichrome, and it's wound around a similar core. Uh, they use those for high power because they can handle, depending on the size of the wire and the size of the resistor itself, they can be made to hand up to, 10, 20 watts, maybe more. Usually you see like 5, 10, maybe 20. Because of the fact that they're made with a coil of wire, they're also an inductor. So they're really only used in low frequency applications like power supplies, things like that that are running at low frequencies where the inductance won't have any significant effect. Here's a picture of some typical kind, and they're all labeled with these color codes, which tells you the value. It's called the RETMA code. It's the Radio Engineering Technology Manufacturers Association or something like that. Over here on the far right, these two are wire wound resistors. And you can see this is a 5 watt, and this one looks like a 4 watt. The rest of these are kind of standard. These more cylindrical ones are older carbon composition. Question? The symbol for a resistor, which we've been through, is this little zigzag. And over on the left, excuse me, and these are much bigger than real, are surface mount. And this top one, that's 3.1 millimeters. That's a little less than 1/8 of an inch. So you can see they're pretty small. I tried doing some soldering of some of these 603s and 402s on a practice board, and it's all you can do to see them. The capacitors, the most common type you're going to find are ceramic because they're very cheap. They're easy to make. It's just two metallic plates, with a ceramic dielectric between them, and then some coating on it. The mica have been around for ages. They're very high Q, which means they have very low resistance and inductance. They're actually made with the mica as the dielectric, which is actually a mineral. It's kind of a crystal-like thing that they can split off in these little thin sort of wafers. They don't make those in the surface mount, so you really only see them in older radios or some of the external circuitry where you can use what they call through-hole components. Paper capacitors are similar. They're older type. It was actually two pieces, long strings of foil separated by some type of paper and rolled up into a cylinder. Tantalums use a kind of a special, it's not quite an electrolytic because they're not polarized, but it's a chemical composition. Polystyrene are the lowest loss capacitors. Again, they don't make them in the small sizes, and they're actually just made out of foil wrapped up around polystyrene plastic. And they actually are, you can actually see through them. They're just clear plastic. Electrolytics are similar to the paper, except instead of just plain paper, it's a paper that is soaked in some sort of electrolytic chemical. So you can get extremely high capacitances for a given volume. They're polarized, so you can only use them in DC circuits. If you apply a lot of AC on them, you can blow them up like a firecracker, which we used to do in school. And they really make a mess because you have little bits of paper flying all over the place that has that electrolyte on it. The main thing to remember is capacitors. The ceramics are the lowest cost, so that's why you see mostly ceramic, particularly in the surface mount. And electrolytics are there when you really need a high capacitance, like in a filter power supply or audio amplifiers where you need high value capacitors. Over on the right are a picture of some typical types. The larger ones, like the blue one, that's an electrolytic. The little black one is an electrolytic, and these smaller ones over here, the kind of orange and brown colored ones, and probably this blue one are ceramic. I'm not exactly sure what the green one is. I can't read it, but it's not a ceramic type. It could be mylar or something like that. And then we also have some variable capacitors, where it's actually two plates, and one of those plates rotates. So as you rotate it, you can either have the plates fully meshed or where they're fully separated. Oh, didn't it come back? And over on the left is just a symbol of a capacitor, showing the charge on the two plates and the dielectric in the middle, and how the charge on the dielectric is distributed. I think in reality, these atoms in the dielectric actually become dipoles, where the charge on the plates will attract the electrons over to one side of the atom. So instead of them running around in this little sphere, they tend to go more to one side, so it becomes kind of a oblong shape or elliptical shape. So one end of it tends to be negative and the other tends to be positive. That's not on the test, by the way. Inductors we've talked about, and they're just coils of wire, either just wound with an air core or wound with some sort of powdered iron or ferrite, or in the case of a power transformer, it would be actually laminations of iron to handle the power. One of the things to remember is an inductor will look like an inductor up to the frequency where it becomes self-resonant. What that means is, in the real world, it's not a pure inductor. It will have some parasitic capacitance. The space between the coils acts as a capacitor. So you'll have distributed capacitance that look like a parallel resonant circuit at some frequency. Once you go beyond that frequency, it does a phase shift and it looks like a capacitor instead of an inductor. The same thing happens with capacitors. As you approach the resonant frequency of a capacitor, because they'll have some inductance, they start to look like inductors at frequencies above their self-resonance. That's one of the things you have to take into account if you're designing circuits, of where those self-resonant points may be. So you don't want them to be where you'll be operating. Most of the inductors in radio circuits today typically will be on toroidal cores. Looks like a little donut or a lifesaver. And they do that because they can get larger values of inductance than you can if it's just air wound. The core material will determine the value of inductance you can get per turn, and also the frequency range that it'll operate over. And that's controlled by the mix, and the material is actually a mixture of kind of rare earth materials. They're various compounds, but they have specific mixes like 31, 43, 61, and they all have different frequency ranges where they will operate. The other thing about a toroidal core is it retains or it constrains the magnetic field almost entirely within the core itself. So you can have two of these next to each other and there's very little interaction. If you had regular air core coils, if they're close together, you'll have the magnetic fields interacting. There's your typical, we call that a solenoid type coil. And this core can be powdered iron or ferrite, or actually some other, in some cases, it could just be phenolic just to hold the shape where it's not actually affecting the inductance. And remember, the symbol is kind of representing these little coils. There's some real world ones. Here's the toroid up here in the top left. These are some surface mount types. This is what we call a through hole. It looks like a resistor, but they're marked differently. And this is a wire wound one on a little bobbin, but it's got some shrink wrap so you can't really see it. And this is another one. I can't tell. It could be a transformer, have two windings, or it could just be an inductor. Any questions on the basic components? Okay, so we'll start talking about solid state device components or devices. So these are composed of what we call semiconductor material. You have resistive material, which doesn't conduct very well. And you have conductors like most of the metals, copper, aluminum, silver, they conduct very well. It turns out you can have a class of material, and silicon and germanium and a few others happen to be in this, what they call a semi-metal, semiconductor material. And they learned that you can essentially enhance this characteristic by what they call doping. So if you take a piece of silicon, and they grow silicon as large crystals, and they machine very thin slices, and you'll see these big round white things, which are silicon wafers that they use in processing. And they will and they use different processes, but in these processes, these doping processes, they will add another material. So in this case, over on the left, we will dope it with phosphorus atoms. And those phosphorus atoms work their way into this silicon crystal matrix. And because in the case of phosphorus, it has one more electron than silicon does. So you wind up with extra electrons in this matrix, which makes it an N-type material with a negative charge all by its own. We do the similar thing with the P-type, where we take the silicon wafer and we add something like boron, which has a fewer electrons. So we wind up with a hole. And we call that a p-type material. So we can use the N material and the P material to make semiconductor devices like diodes and transistors, which we'll talk about next. So if we take a piece of N material and a piece of P material, and they join them together, we call that a p-n junction. What happens?
Robert, just to make sure I understand the p-type material is positive?
Correct.
Okay, just making sure. Okay.
It's positive and it has holes.
Okay.
And those little plus signs are the holes.
Gotcha.
Where the N region has free electrons. So the the holes in the P region are attracting electrons in this area we call the depletion layer, which is right at the junction between the two. And the N region is attracting holes, basically. And the effect is it becomes kind of a no man's zone. And there's a positive charge between the N region and the P region in this zone. It turns out in the case of silicon, that charge is approximately 0.7 volts. If this was germanium material, which you do the same kind of stuff with, but germanium isn't used very much except for some diodes. The voltage, if this was a germanium diode, would be 0.3 volts. Now, the reason that's important is for you to get current to flow from the P region to the N region, you have to overcome this bias voltage. So if you apply a voltage between this end and this end, and it gets up to greater than 0.7 volts, current will actually flow from the P to N region. And that makes a diode. So here you can see the P material, which has a electrode connected to it, and the N material has an electrode. So that makes a two electrode diode. We call the positive end the anode, and the negative or N material end the cathode. And we use this symbol of the triangle and a bar to represent the diode, the bar being the cathode end or the negative end.
Obviously, I had to do it before I went into the meeting. Can you do me a favor? Charge that part up. Oh, I'm sorry. I didn't realize my microphone was back on. I apologize.
No problem. Did you have a question? Okay. On most of the diodes, they're going to have a stripe on one end, a white stripe or a black stripe, depends on the body of it, that indicates the cathode end. They won't all be that way, but the majority of the smaller diodes are going to have a stripe to indicate the cathode. And remember that if it's a silicon diode, it requires 0.7 volts for it to start to conduct. If it's germanium, it requires 0.3 volts. And the stripe on the cathode end, obviously they're red because there's questions, and those are the answers.
Yeah.
Here's a plot showing the forward and reverse voltages on the diode. In a real diode, there's actually a little bit of leakage current. It's very small, usually in microamps, until you get up to this knee, which in the case of silicon is the 0.7 volts, and it starts to conduct. And it rapidly goes up, and the slope of this line turns out to be the actual amount of resistance in the diode. So the lower resistance that diode is, the higher the slope and the more current it will carry. Now you also notice if we apply a negative voltage, we shouldn't have any current flow, but once again, there's a little bit of leakage. Here they're saying it's less than 20 microamps if it's a silicon device. But when we get to a certain point called reverse breakdown voltage, there's this thing they labeled the Zener effect. I think it was some guy named Zener that discovered it. And it just sort of avalanches and conducts in the opposite direction. And it's very precise. They can actually manufacture diodes, and we'll call them Zener diodes, where they control where this breakover point is to less than a percent. And that's used a lot for a voltage reference or in power supplies where you want some sort of known voltage. You just add a resistor to it, reverse bias it, and you'll get that Zener voltage between the diode and the resistor. And in all these, remember, we're talking about conventional current flow from positive to negative, where in reality, electrons flow from negative to positive.
Could you just clarify, because I get mixed up on this when it talks about like the germanium type has that forward voltage drop.
Uh-huh.
What does that mean, the words forward voltage drop?
Well,
For both the silicon and the germanium. Is that negative to positive?
positive to negative.
Positive to negative. Okay.
Right. Where reverse is be negative to positive.
Gotcha. Okay.
And we call that conducting in the forward direction.
In the forward direction, from positive to negative.
Correct.
Okay.
With conventional current.
Well, let's don't complicate that.
Well, it's what you've been taught. It goes
Yeah.
positive to negative.
Okay.
There's a lot of things you've been taught that aren't exactly correct. And
Okay.
Benjamin Franklin actually decided that that was positive and this was negative. They didn't know any better.
Right.
Okay, so one of the practical uses of diodes, not just semiconductor diodes, but vacuum tube diodes and metallic, which are made by putting layers of copper oxide and selenium together. And it only it's a diode. It passes current in one direction when it's forward biased. That's used in power supplies where we can take the AC voltage from a transformer. Say this was a step down, like we talked about last week, where 120 volts on the primary and 12 volts on the secondary. If we put a diode in the loop prior to the load, we're going to see it conduct on the positive half cycles of that wave. So we'll get these DC pulses. And if we run that through a filter capacitor, we'll get kind of a constant DC value. If we add, I'll complicate it a little bit. If we added a second diode on this leg and a center tap here, we'd have a full wave rectifier, and we'd pass both halves, the positive and the negative, and they look like positive pulses. So it would be, instead of 60 cycle ripple, we'd have 120 cycle ripple. So it's easier to filter. Okay, so now that we've got a diode, somebody decided, well, what if we take a third piece of semiconductor material and add it, and maybe we can do something useful. So they came up with a what we call a bipolar transistor by taking our PN junction diode and adding another piece of N material on the other side. So now we have an NPN sandwich. So we have three pieces of material and we have three connections. So now we call the P material in the middle the base, and the N material, when it was a diode, instead of a cathode, we now call it the emitter. And the new piece we call a collector. And these are all based on conventional current flow. So that's why the collector is getting the current that's coming out the emitter. Okay. Like I said, it's actually electrons going the other way, but we don't want to confuse you yet. You can also have the opposite, where I have a PNP, where the N material is in the middle. So it still operates the same, but the opposite. It takes a negative voltage as opposed to a positive voltage. The NPN are going to be the most common of the bipolar types. So by adding that third piece, we now have a device where we can control the current flow between the collector and emitter. Because if I think of this diode, the PN junction, where I apply a voltage to the base or the P material, I get current flow if it's more than 0.7 volts, if this is a silicon device. When that happens, and I'm not going to go into how, it causes additional current to flow through this other piece of N material out through the collector at a multiplier of the current that's going through the base emitter. And we call that gain. Sometimes they label it something like HFE or transistor gain. It's typical that is anywhere from 50 to maybe a few thousand. So in other words, if I had a milliamp going through here, I could have as much as an amp current flow through here. So by regulating the amount of current through this base emitter junction, I control the amount of current that can flow between the collector and emitter. So I can either use that as an amplifier or as a switch, which we'll talk about in another slide or two. Now, there's also another type of transistor. We still use the same kind of semiconductor material, but we build them slightly different. There's a class called junction FETs, or junction field effect transistors, where we have the same three pieces of material, like in the case of the N channel, it would be NPN. And we, instead of the base, we label that the gate. And instead of the emitter, we label it S for source and D for drain instead of collector. And now these are labeled because electron flow comes in the source and goes out the drain, just to confuse you. So they got wise when they invented the field effect transistors and started talking about actual electron flow. It works similar, except there's no current that flows between the gate and the source. It's strictly the voltage because it creates an electrostatic field, and it's that field that controls the current flow between the drain and the source. And again, you can have opposite polarity. You can have P channel, which would be PNP sandwiches. You can also have this NMOS class, which is called a metallic oxide semiconductor, both in N and P. And here, this gate, instead of actually having a junction, is insulated by some kind of like silicon oxide, some sort of metallic oxide. So there's actually no electrical connection at all. It's just the electric field that gets created. The main thing that you need to remember on the transistors, they're all three terminals. The controlling terminal, either the base or the gate, controls the flow of current between the other two terminals. And in bipolar, we labeled them base, emitter, collector. And for field effect, regardless of the type, they're gate, drain, and source. Any questions on those?
So you said the base and the gate control the flow.
Correct.
Okay.
And in the case of bipolar, it's the base current. In the case of the field effect, it's the gate voltage. You'll actually find that the field effect operates similar to a vacuum tube, which I think we talk about next, or in a bit. This is a kind of a slice of how a typical bipolar junction transistor is formed. So here we have your sort of your diode with your PN junction, and then this collector is formed around it. Actually, they have the collector material, and I don't actually know the process, but they embed these other two within it and then make the connections. These are actually done most of the time with little gold, very fine gold wires that are welded onto these sections. So the main advantage of doing this is they discovered that a very small current is able to control a very large current, or in the case of the field effect, a very small voltage can control a very large current. So that allows us to use it as a power amplifier or a voltage amplifier, or as a switch. So when we use it as an amplifier, we try to operate it in what's called the linear region between cutoff and saturation, where the input current through the base is going to give us a proportional current output through the collector emitter. And in this typical amplifier circuit, this is what we would call the load resistor, this RC. And that's resistance is the slope of this line, which is going between whatever the maximum voltage would be and the maximum current. And you can see 2 points that are marked on here. Actually, this one, the way they drew it, is very misleading. Saturation is the point where, regardless of how much base current you keep adding, you're not going to get any more collector to emitter current flow. It's saturated. In the case of using it as a switch, it's fully on. It's conducting as much as it can possibly conduct. The cutoff region is the smallest amount of base current, typically at 0, where you have 0 to almost no current flow from collector emitter. So that would be like the switch being open, and this would be the switch being closed. When we want to operate as an amplifier, we try to pick and operate, we bias the base voltage to operate like somewhere along here. So as the base current changes, we'll operate along this load line, and that will be the current flowing through the device, either almost 0 or almost the full amount. As we get closer to these, it becomes less linear. That's why we tend to operate in the middle and limit the amount of excursion to keep the device linear. Does that make sense?
Yes.
Okay.
Part of it.
To me, it's very confusing, but I get this, I get the idea where you're going, but I just don't see the reality of it. You know what I mean?
Okay.
I get the theory.
Well, as far as the questions, you only need to remember amplifiers operate in the linear region and switches operate between cutoff and saturation.
Okay.
So we talked about field effect transistors. And here's a kind of a cross section. This happens to be a metallic oxide, where you have this oxide layer, which is an insulator between the gate and the body. And you have so this is your NPN, or an N-channel MOSFET. And when you apply a voltage to the gate, it creates an electrostatic field between the gate across this oxide layer and the body. And the strength of that field controls the amount of current that can go between the source and the drain, or the electrons that can go from the drain to the source, however you care to look at it. So as you increase and I'll just probably get them backwards. I think in this one, as you increase the field, you increase the flow, and in the opposite polarity, where it's a PNP, you get the opposite effect. And it's called like a pinch effect. It's kind of hard to describe, but basically, you have to remember that field that's created by the gate voltage controls the amount of current that flows between the source and drain, similar to the way the base works on the bipolar. The junction field effect is similar, but construction is slightly different. For the general exam, you really only have to know about metallic oxide semiconductors and what the metallic oxide stands for. Okay, so now we get to vacuum tubes. Vacuum tubes are still around. Probably half of the power amplifiers are still vacuum tube amplifiers. Older radios, there are a lot of them still around. People like to collect the old stuff. It still works fine, all made with vacuum tubes. One of the advantages of the vacuum tube is it's not really susceptible to EMP, where the solid state devices with the large EMP won't work anymore. So that's another reason for keeping vacuum tube devices around. The first vacuum tube or electron tube, or as it's called in Britain, valve, was done by, I forgot his first name, a guy by the name of Fleming, and it was called the Fleming valve, and it was a vacuum tube diode. And they discovered by heating the cathode element, it would emit, to get it hot enough, it would emit electrons, and like an electron cloud around that cathode. And the other device, because it's a diode, we call an anode. We change it to a plate when we make it a triode or tetrode. Would attract those electrons with a high enough voltage, and you would have electrons flowing from the cathode to the anode, just like in a diode, where we would say conventional current was flowing from the anode to the cathode, but it's really those energized electrons that were ejected from the cathode that are being attracted to the anode. They then discovered that if you added what we call a control grid, which is just physically some wires in the path between the cathode and the anode, by applying a voltage to those wires, we can create a field, like in the field effect transistor, and these came first, that will control the flow of electrons between the cathode and the anode. Although here we decided to rename the anode to the plate. So the control grid, similar to the gate or the base, controls the current flow between the anode and the cathode, or the plate and the cathode. And it's done by applying a voltage to the control grid. And that first triode, we call this, with a control grid, is I just had his name. Oh, Dr. DeForest came up with that. and invented the first triode. And here's a kind of a symbol where we're applying a voltage to the control grid. They're not showing the filament that heats the cathode and a high voltage on the plate. Now, one of the things that's also different about vacuum tubes, they operate at much, much higher voltages than semiconductor devices. So a typical triode in a radio, this plate voltage may be 200-300 volts. In a power amplifier, 3, 4, 5,000 volts. So everything is much higher voltage. At some point, they discovered one of the limitations of the triode was the fact that because we have this plate and we have these wires, we also have a capacitor. And it's called the grid to plate capacitance. That limited how much we could use this as an amplifier and also the frequency range that it would operate over. Because this capacitance would start to act like a low reactance between the grid and the anode, and eventually at a certain frequency, you really wouldn't have any control at all. You'd be passing current, but you'd have no control over it. So somebody came up with the idea of adding yet another grid. They call it a grid because it's just a grid of wires. And they call this a screen grid. And what that does, if you remember when we talked about capacitors last week, what happens when you put two capacitors in series? It reduces the capacitance so that it's less than the lowest of the two or more values. So by adding a screen grid, I now have another capacitor in series with the control grid. So I've cut the capacitance down dramatically, anywhere from around 8 picofarads to maybe as low as a quarter or a 0.025 picofarads, which allows me to operate this tube at much higher frequencies than I could the triode. So the main takeaway here is the screen grid is there to reduce the control grid plate to capacitance and also increase amplification, but mostly for the capacitance effect. Everybody clear on that one?
Yeah.
I think so.
Well, we'll find out in a bit. So we also have batteries. Why they stuck these with the other devices, I don't know, but they had to put it somewhere. So a battery is just a source of electric power consisting of one or more electrochemical cells. Battery is a chemical process with external connections, obviously, or you wouldn't be able to use it. We use a lot of them in amateur radio. Handhelds have usually rechargeable batteries. Mobile radios in your car operate off of your car battery. It's a lead acid rechargeable battery. Base stations, in a lot of cases, people will set up backup power with either car batteries or lithium iron, usually lithium iron phosphate. And maybe solar panels to charge it so that you can operate if you lose household power. You could have operated your base station last night if you had that set up, Nanette. Portable operation where you go out in the field doing QRP or field day. You tend to operate off of a battery, even if you're operating with a solar panel that's charging the battery, you're really operating off the battery. Some of the common types of the rechargeables, nickel cadmium, they're not used as much anymore. They were great for very high discharge current applications because they had very low internal resistance. The newer lithium ion, lithium poly, especially batteries, also have very low internal resistance and very high discharge current, but they're not on the list. The lead acid batteries tend to be used more for long life applications like your automobile, your storage batteries for your base station, go-karts, things like that, where your boats, you're going to operate for a long time. The one thing to remember about a lead acid battery is that if you let it discharge below 10.5 volts, it will start to damage the battery and it can actually go into cell reversal. Most people think a typical car battery or lead acid battery is, they call them 12-volt batteries. A nominal charge for the lead acid battery is 13.8 volts. So if you ever looked at amateur radio transceivers, they're all designed to operate off of 13.8 volts for that very reason. A charged up lead acid battery is going to be about 13.8 volts, could be a little bit higher, but that voltage will drop very rapidly to 13.8. The non-chargeable batteries that we tend to use are the carbon zinc batteries, like your AAAs, AA's, and C's and D's. They're not rechargeable, but they're very convenient. You just have to have a lot of them if you tend to go on a trip or something and don't have anywhere to charge rechargeable batteries. So the basic takeaways that we don't use wire wound resistors in RF circuits because of the inductance. We use them in audio frequency or power circuits. And as far as capacitors, the ceramic are low cost, stable values. The electrolytics give you a high capacitance for a given volume. If you noticed on those pictures, they weren't a lot larger than some of the other, I don't remember if they had any of the paper type and stuff, but you can get electrolytics. I have some that are 10,000 microfarads. I think they go beyond that. They start to get big, but remember that inductors can turn into a capacitor. Basically, if you operate them at a frequency above their self-resonant frequency. Toroids give you a large value of inductance compared to just an air-wound coil. You can optimize the property of the toroid, like frequency response, based on the mix of the material, and that the magnetic field is almost totally contained within that toroidal core. There's very little stray magnetic field. When we use a diode as a rectifier, we're it's called that when we're using it to convert AC to DC. It's still a diode, but in that application, we call them rectifiers. In the case of solid-state diodes, remember that germanium, and this goes for transistors also, has a 0.3 volt forward threshold voltage, and silicon has 0.7 volts. In the transistors, remember that a MOSFET stands for metallic oxide semiconductor field effect transistor. And the gate, or the control element, is separated from the channel that has the source and drain with some sort of metallic oxide insulator. And when we use the transistor as a switch, we operate it between either at its cutoff or its saturation. Between doesn't mean linear in between those. It's either at cutoff or at saturation. So you apply, in the case of a bipolar transistor, you would apply either 0 base voltage to have it at cutoff, or you would apply enough voltage to get up to the saturation current, where it would be on. In vacuum tubes, the control grid is what we call the regulating element, and it regulates the electron flow between the cathode and the plate. And in the case of a tetrode, because we've added a fourth element, we call it the screen grid, is there to reduce the control grid to plate capacitance. In the case of batteries, we use both rechargeable and non-rechargeable. You need to remember which is which. Nickel cadmium has extremely low internal resistance, so it has a very high discharge current. Probably more than a lead acid battery, which has a lot. If you short the cells on a lead acid battery, it can produce enough current to actually cause an explosion. The lead acid battery shouldn't be discharged below 10.5 volts, or it will start to damage the battery where you can't recover it. So let's see how much you remember. Why should wire wound resistors not be used in RF circuits?
You said unpredictable. Bravo.
Sounds good. Which of the following circuits is characteristic of low voltage ceramic capacitors?
They're low cost.
Right.
Delta.
Right. The surface mount ones are typically a few cents a piece. In bulk, they get down to maybe 1/100th of a penny each. What happens when an inductor is operated above its self-resonant frequency?
It becomes a capacitor. So Charlie.
Charlie? What's the approximate forward threshold voltage of a germanium diode?
Germanium's 0.3.
Bravo.
Bravo.
Correct. What's the approximate forward threshold voltage of a silicon junction diode?
Charlie.
Charlie.
What are the operating points for a bipolar transistor used as a switch?
Alpha.
Bravo.
Saturation.
Wait. Oh, yes. Yeah, I'm sorry. Well, let me read it again.
They're trying to trick you.
I say bravo. They kept saying between, and then you had to clarify what between meant. So,
Well, yeah, obviously I didn't clarify it.
because you were saying it's not between, it's actually at saturation or at cutoff, but they kept using
Correct.
the word between.
Yeah. That's I'll have to go look at that chart.
So it's alpha,
Yes,
obviously alpha, but
it's alpha, right?
yeah.
It operates either at saturation or cutoff. An amplifier
Okay.
is going to operate somewhere between saturation and cutoff.
That's why I didn't think it was Bravo, because that's what you said, amplifier,
Right.
which I bet is be a question later.
Which of
Oh,
the
God.
following describes MOSFET construction?
Bravo.
Bravo.
Which element of a vacuum tube regulates the flow of electrons between cathode and plate?
Alpha. The control, not the screen.
Alpha.
Right.
Alpha.
What's the primary purpose of a screen grid in a vacuum tube?
It's
Charlie.
capacitance. I don't know.
Control the grid.
Alpha? Did you say capacitance, not resistance?
Hmm. Yes, alpha, alpha. I'm thinking the other one. Alpha.
Right.
Yes.
Because you're putting two capacitors in series. So you're reducing the capacitance.
Yeah, that's when you're at that. So.
What is the minimum allowable discharge voltage for a maximum life of a standard 12-volt lead acid battery?
Charlie, 10.5.
Charlie.
So if you ever let your car battery discharge down below that, you're probably going to look at a new battery. Or it's not going to hold as much charge as it used to. What's the advantage of batteries with low internal resistance?
It's low resistance that has a high current going out. So bravo.
Right.
Is that right?
Right.
That's correct.
No.
So you got 12-volt battery and it's got low resistance in the output. You'll get more current than you would if it had a high resistance.
Right.
All right, you guys did great.
Easy for you to
A
say.
couple of them were tricky, but
And I even remembered to record,
yay.
I think. I must have, because it's going to let me stop.